What if a whisper from another galaxy could rattle Earth's planetary defenses? On October 1st, 2025, something 2.5 million light-years away seemingly touched our planet's invisible armor, triggering a scramble inside NASA. This wasn't a solar storm we could predict. It was something entirely new, linking the distant Andromeda galaxy to the radiation belts that shield us all. We're going to break down the signal, the response, and what it means when the cosmos reaches out in unexpected ways. Let's explore this together.
The October 1st discovery.
It began as a day like any other inside NASA's Space Weather Prediction Center. A standard G2 geomagnetic storm watch was issued, implying a KP index of 6 on a scale of 9, but the source was a predictable solar magnetic cloud. But then, the routine broke. At Goddard Space Flight Center, mission controllers noticed odd chatter. Automated queries to the legacy data from the Van Allen probes, officially the Radiation Belt Storm Probes or RBSP mission, began spiking. Someone, or something, was digging through recent radiation belt telemetry, and fast. The access patterns weren't for routine analysis. They matched emergency protocols designed for rapid threat assessment. Whispers started surfacing online. Signals from the Andromeda galaxy, our planet's protective radiation belts, had blinked, and though NASA remained silent publicly, the digital evidence told a story of a new and unexpected cosmic connection. Experts like Dr. Antti Pulkkinen, a renowned heliophysicist at Goddard, would have been among the first to be alerted to such a deviation from established models. The first sign that our understanding of space weather was about to change had arrived not with a bang, but with a series of urgent automated database queries.
The anomalous signal.
Here's what started the entire chain of events. At 3:47 UTC, the Deep Space Network nodes in Goldstone, California and Canberra, Australia, logged a strange radio transient. It lasted only 8 seconds and came directly from the Andromeda sector, a tiny patch of sky less than a degree across. Instantly, it stood out. The signature didn't match any known pulsars or the behavior of cataloged quasars. For a normal solar radio burst, the pattern was all wrong. The signal's intensity, while faint at a flux density of only a few Janskys, was coherent enough to be unmistakable. But the most compelling clue was its frequency. The burst peaked at 408 MHz. That's a softer, lower frequency than most fast radio bursts, or FRBs, which typically hit between 600 and 1400 MHz. This detail is critical because lower frequencies like this are known to be in the range that can efficiently interact with and stir up electron motion within Earth's magnetosphere, a process governed by plasma physics. This wasn't just random noise from deep space, it was a signal with a frequency that, theoretically, was perfectly tuned to get a reaction from our planet's protective shields. It was a whisper, but it was a whisper at exactly the right pitch to be heard.
The belt response.
16 minutes after that anomalous signal from Andromeda was detected, something happened much closer to home. NOAA's GOES satellites, sitting in geostationary orbit 35,786 kilometers above Earth, registered a sharp 40% jump in electron counts. Specifically, their magnetospheric electron detector, or MAGED instrument, saw a surge in relativistic electrons with energies greater than 2 mega-electron volts. This wasn't a slow swell you'd expect from solar wind. It was a violent spike in under 3 minutes, 800 times faster than the baseline activity on a quiet night. Ground magnetometers in Tromsø, Norway, and data from the Canadian Charisma Network confirmed the fluctuation. The timing was too perfect to be a coincidence. An 8-second radio burst from a galaxy 2.5 million light-years away, followed 16 minutes later by a significant measurable disturbance in the radiation shield protecting our planet. The data was undeniable. Something had reached across an unimaginable distance and physically nudged the Earth's magnetosphere. The invisible armor of our world had been touched, and now the race was on to understand how. It was a direct challenge to every existing space weather model.
NASA's response protocol.
When Earth's radiation belts move that fast, and, the sun isn't the obvious culprit, NASA doesn't guess, it executes a playbook. The first call goes to the Space Weather Coordination Center. Step 2 is to pull real-time solar wind data from the DSCO-VR satellite, which sits 1 million miles from Earth at the L1 Lagrange point. Its Faraday Cup instrument showed solar wind speeds were a placid 385 kilometers per second, with the interplanetary magnetic field's BZ component hovering near zero, no southward tilt that would open a door for solar energy. Step 3 involves comparing magnetometer readings from a global network, from Alaska to Antarctica. On October 1st, none of these standard checks provided an answer. The DST index, a measure of geomagnetic storm strength, was a negligible -8 nanoteslas. With no earthly or solar explanation, the situation was escalated to level 2. This means waking up principal investigators, running predictive models on supercomputers, and immediately checking the position of astronauts on the International Space Station and high-value satellites. The scramble isn't chaos. It's a methodical checklist running against a terrifying new variable, leaving forecasters with data they couldn't explain.
The physics mystery.
The data left researchers with a series of profound questions. First, the timing offset. The belt's twitch lagged the radio burst by exactly 16 minutes. Since electromagnetic waves travel at light speed, a direct cause and effect should have been instantaneous. This delay suggests a secondary mechanism. Maybe the burst triggered a cascade effect in the plasma waves already surrounding Earth. Second, the frequency mismatch. The Andromeda burst's peak at 408 MHz is unusually low, but it happens to fall squarely in a frequency band known to efficiently transfer energy to trapped particles via Whistler mode chorus waves. Finally, the signature of the disturbance itself. Data hinted at a sharp change in pitch angle distribution, essentially how steeply electrons spiral along Earth's magnetic field lines. This suggests they were scattered by a wave pulse, knocking some from stable orbits into the loss cone where they precipitate into the atmosphere. Experts in this field, like Dr. Richard Thorne of UCLA, have built entire careers modeling these wave-particle interactions. These three clues, the delay, the resonant frequency, and the scatter signature, pointed away from coincidence and toward a new, unmapped physical mechanism.
Historical surprises.
To understand the shock of this event, you have to know that the Van Allen belts have a history of shattering our assumptions. In September 2012, NASA's Van Allen probes discovered something thought to be impossible. A third, temporary radiation belt materialized between the two known belts, located at an L shell of about 3.5. It lasted for 4 weeks before a solar shockwave erased it. The lead investigator, Daniel Baker from the University of Colorado's Laboratory for Atmospheric and Space Physics, stated plainly that our models were wrong. Then in 2014, the same probes found what scientists now call the impenetrable barrier. At an L shell of 2.8, or about 11,000 kilometers altitude, the most energetic, ultra-relativistic electrons with energies above 5 mega-electron volts simply stop, unable to move closer to Earth. And as recently as May 2024, the SERB-C CubeSat mission confirmed the formation of 2 temporary extra rings, which persisted for months. For over 60 years we've studied these belts, yet they repeatedly prove we don't have the complete picture. They can reconfigure in ways we can't predict, responding to forces we are still struggling to identify.
The resonance mechanism.
So, the leading theory to explain this event doesn't, involve a powerful blast from Andromeda, but something far more subtle: resonance. Imagine, if you will, pushing a child on a swing. You don't need immense strength, you just need to push at the right moment, matching the swing's natural frequency. The Van Allen belts are, a resonant system. The trapped particles and magnetic fields have natural frequencies, governed by a process called cyclotron resonance. Researchers like Dr. Wen Li at Boston University have created models showing exactly how specific wave frequencies can pump energy into the electron population. The Andromeda signal, despite traveling 2.5 million light-years, didn't need to be overwhelmingly powerful. It just needed to hit the right note. The burst's 408 MHz frequency may have perfectly matched a natural resonance frequency in the outer belt's plasma. This would allow electrons to efficiently absorb the energy, causing them to change orbits and scatter. It's not science fiction, it's a proven concept. The only question is whether a signal from another galaxy could really be the trigger.
Real-world consequences.
A twitch in the Van Allen belts isn't just an academic curiosity, it has immediate real-world consequences. GPS satellites orbit at 20,200 kilometers, right in the heart of the outer belt. A sudden 40% spike in electron density can degrade the standard positioning service from 3-meter accuracy to over 10 meters, affecting everything from air traffic control to financial systems. Communication satellites can experience temporary outages, causing dropped calls and buffering streams. For astronauts, especially on future Artemis missions, an unexpected radiation spike is a serious health risk, potentially adding several millisieverts of dosage with little warning. In a worst-case scenario, intense radiation can cause permanent satellite damage, as was demonstrated by the early failure of Telstar 1 in 1962 after being exposed to a man-made radiation belt. The systems our modern world is built on are fragile, and they all run under the influence of these unpredictable belts. This event serves as a stark reminder of that vulnerability.
Testing the hypothesis.
So how do scientists move this from a fascinating anomaly to proven fact? It comes down to a rigorous, repeatable process. Step 1 is timestamp alignment. You overlay the logs from radio telescopes like the CIME-FAR-B detector in Canada with satellite data from missions like JAXA's Arase probe with microsecond precision. If that 16-minute lag repeats, it points to a real connection. Step 2 is a spectral match. You analyze the frequency of future bursts. If they consistently fall within the resonant bands, the case for a physical mechanism gets stronger. Step 3 is multi-latitude confirmation. You need magnetometers across the globe to register the same event, confirming a planet-wide response. But the most critical test is repetition. 1 event is an anecdote, 2 is a pattern, 3 establishes a phenomenon, worthy of publication in a journal like Nature. If another Andromeda burst occurs and the belts don't respond, the hypothesis is weakened. Both positive and null results are crucial. It's the slow, methodical work that separates real discoveries from sensational claims.
Background science explained.
Let's quickly break down the core science. The Van Allen belts, discovered in 1958 by James Van Allen, are 2 primary donut-shaped zones of charged particles. The inner belt, between 1,000 and 6,000 kilometers altitude, is mostly stable. High energy, protons, in the 10 to 50 MeV range. The outer belt, from 13,000 to 60,000 kilometers, is a dynamic zone of electrons. The primary driver of change is the sun. Solar flares and coronal mass ejections blast particles toward Earth, causing the belts to swell. Inside the magnetosphere, a constant dance of wave-particle interactions is happening. Waves with names like chorus and hiss are always accelerating and scattering these trapped electrons. Deep space signals are also arriving constantly. Fast radio bursts are millisecond flashes from distant galaxies. Pulsars are spinning neutron stars that emit regular beams with millisecond timing precision. The October 1st event suggests a new type of interaction, where a specific radio signal from deep space might be coupling with the natural wave physics already happening in our own backyard, a concept previously confined to theory. So, we stand at a fascinating crossroads. An 8-second radio burst from the Andromeda sector, followed 16 minutes later by a 40% spike in Earth's outer radiation belt. The data is documented, the timing is recorded, and the standard explanations, solar flares, magnetic substorms, don't fit. We're left with a working mystery. Was this a 1 in a billion cosmic coincidence, or have we discovered a new way the universe can interact with our world? The answer will come not from speculation, but from the slow, rigorous process of science. Instruments are watching, data is being gathered. The next signal could be the one that confirms it all. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the science that's reshaping our understanding of the cosmos. What do you think is behind the 16-minute delay? Thank you for watching Future Facts.